Okay, once again, good day to each and every one of you. So for today, we will be discussing about work and energy. So if we define work, work is the product between the force magnitude F and also the displacement magnitude D. So we have here our equation for work. Work, we have capital W is equal to force F times the displacement D. So this is our equation or formula for the work done given the constant force which is in the direction of a straight line displacement. Okay, so how about the unit for work? So for the unit of work, we have here joule or capital letter J. So if we have a plural for joule is we have joules. Again, we have capital letter J still. So 1 joule is equivalent to 1 Newton times 1 meter. It's because for the joule, we have using the equation for work. Work is in terms of joule times we have, is equal to, we have the force. Now, the unit for force is we have in terms of Newton or newtons. And then for the displacement, the unit of the displacement is in terms of meter or meters if plural. So that's why 1 joule is equivalent to 1 Newton per meter, or we can also call it as 1 Newton meter. So that is the equivalent for joule in terms of the units of force and displacement. So this one right here. Okay, so how about if our work, if our force is acting at a specific angle with regards to the displacement? So in this figure, figure 6.3, we have here a car moves through a displacement S. So in this case, they are using the symbol for the displacement is S instead of D. But here we will be using D as the variable for the displacement. So the car now moves through a displacement S, which means it is moving horizontally, while a constant force F acts on it at an angle phi or phi. So this is the angle right here to the displacement. So now, when it comes to force, since our force is at a specific angle phi, we need to break down force into two components. So here we have the parallel force and also the perpendicular force. But here it is mentioned na the perpendicular force does no work on the car. Now, why is it that perpendicular force does no work on the car? It's because if you are exerting a perpendicular force to the car, it seems na instead of pushing the car with regards to or on the same direction to as the displacement, perpendicular force here is like lifting the car upwards. So perpendicular force or 90 degrees with regards to our displacement. So that's why perpendicular force does no work on the car, because if you are exerting a perpendicular force, you are lifting the car upwards, which means that the car will not move at a specific displacement because the force that you are exerting is a perpendicular force. Whereas, if we are exerting a parallel force, again we will say parallel, it is on the same orientation with our displacement. So only parallel force does work on the car. So that's why we have here for our equation for work, work is we have is equal to the parallel force times the displacement. Or if we will substitute the value of parallel force, which is equal to F times the cosine of the angle phi or phi, so we have work is now equal to force times the displacement times the cosine of the angle phi. Or if we will have it in terms of dot product, we have work is equal to the dot product between the force and the displacement. So we have again two equations. For the single line displacement, we have work is equal to force times the displacement. And if we are dealing with a force acting at a specific angle, we have work is equal to force times the displacement times cosine of the angle phi or phi. Okay, so we have here an example. First example for work. Steve exerts a steady force of magnitude 210 newtons on the stalled car as he pushes it a distance of 18 meters. So the car also has a flat tire. So to make the car track straight, Steve must push at an angle of 30 degrees to the direction of motion. So this case is for letter A. So since we have letter A and letter B, this situation here is for letter A. So here the question is, how much work does Steve do? Okay, so for letter A is we need to solve for the work done by Steve on this stalled car. So before we proceed in solving for the work done, we will first write all the given values that is provided by the problem. So the first value is here we have the force of magnitude 210 newtons. So we are given the value for force, which is 210 newtons. Also, we have here distance, which is 18 meters, and also an angle of 30 degrees. So we have the angle phi or phi, which is 30 degrees. Okay, so according to the given, we have the force, the distance or the displacement, as well as the angle phi. So here we have two equations for work. We have the work in a straight line displacement. We also have the equation for work of the force at an angle or at a specific angle with regards to the displacement. So since we are dealing with the angle here, so we will be using the equation work is equal to force times the displacement times the cosine of the angle phi. Okay, so we have now the value for force, the value for the distance, and also the angle theta, so we can now solve for the work done. Okay, so substituting the values, we have force is 210 newtons, distance is 18 meters, and then times the cosine of 30 degrees. Okay, so if we will use a calculator to solve for the work done. So we have 210 times 18 times the cosine of 30. Work is equal to, we have 3,273.58. And then we have here our unit for work is again in terms of joules. So the work done by Steve on the stalled car is equal to 3,273.58. So again, that is the work done by Steve on the stalled car. Okay, so now we will proceed with letter B. So for letter B, it is another situation. So in a helpful mood, Steve pushes a second stalled car with a steady force. So now here, notice that our force as well as our displacement are both vector quantities. So given, let's write the given first. So we have the force, vector force F is equal to, we have 160 newtons I hat minus we have 40 newtons J hat, and then we have for the displacement we have 14 meters I hat plus 11 meters j hat. Okay, now who are this I hat and j hat? And what are their roles in a vector quantity? So here, I hat and j hat are what we call the unit vectors. So unit vectors, when we say unit vectors, they are the indication or the indicator of the direction at a specific axis. So we have again I hat and j hat on this case. So I hat is for the x-axis, is the unit vector assigned for the x-axis, and j hat is the unit vector assigned for the y-axis. So also if we have a z-axis, or if we are dealing with three-dimensional vectors, we have, for the z-axis, we have k hat. Okay, so here it means na, let's say for example, as a force, 160 newtons I hat means that we have a magnitude of 160 newtons and then on the positive x axis. So the I hat here is an indicator of the direction together with your magnitude or with the value, because again a vector quantity has both magnitude and direction. Okay, so now let's go back to the question. So how much work does Steve do in this case? So again, we will solve for the work done by Steve on the second stalled car. Okay, so now here, how can we solve for the work done given the vector force and the displacement in vector form? So if we will break down the force and the displacement into x and y components, so we have here our f sub x is, we have 160 newtons, because again we have an indicator here, the I hat, which indicates na si 160 newtons is located along the positive x-axis. So obviously this is our f of x or f sub x. And for our f sub y, we have negative 40 newtons. So we have right here negative 40 newtons j hat. So it means na we have a magnitude of 40 newtons and then on the negative y-axis. So we have negative j hat. So that is for our force in terms of x and y components. Now, also for our displacement, we have d sub x and d sub y. So our d sub x here is 14 meters and our d sub y is 11 meters. Okay, so how can we solve for the work done on this case? So to solve for the work done, we will be getting the total work done, which means na we will get the sum of the work on the x-axis and the work done all along the y-axis. So from our equation, work is equal to force times the displacement. So for the work done along the x-axis, we have force on the x or along the x times the displacement on the x-axis plus we have the force on the y-axis times the displacement along the y-axis. So since we have the following values for the x and y components of the force and the displacement, so we can solve for the total work done. Okay, so substituting the corresponding values, we have f sub x is 160 newtons times d sub x is 14 meters plus we have our f sub y is negative 40 newtons times d sub y is 11 meters. Okay, so we have right here 160 times 14, we have 2,240 joules. And then for our y components, we have negative 40 times 11, which is negative 440 joules. So we have 2,240 joules minus 440 joules. So our total work done, the total work done by Steve on the second stalled car is equal to 1,800 joules. So this is the work done by Steve on the second stalled car. So again, from letter A, notice that the work done by Steve on the first car is 3,273.58, while on the second stalled car, Steve exerted a work which is equal to 1,800 joules. So that is for example number 1. Okay, now, so how can we know if our force, our work is positive, our work is negative, and our work is 0? So we have this following situations. We have 3 situations right here. For the first one, letter A, we have our work is positive. So when will our work be positive? So work is positive if our force F has a component that is in the same direction with the displacement. So looking at the figure or the situation right here, our force that we exerted is on the same direction with our displacement S. And also, our angle phi must be greater than 0 but less than 90 degrees. Kaya naman, it's because cosine of 90 will be equal to 0. So there will be no work done if our force is or if the angle of our force is equal to 90 degrees. So it must be greater than 0 but less than 90 degrees. So that is the time na our work will be positive. So it must be on the same direction with the displacement, or our force must be on the same direction with our displacement, as well as our angle phi must be greater than 0 but less than 90 degrees. So that is how we will know if our work, when our work will be positive. Now, how about when work is negative? So the value of your work is negative if our force has a component that is opposite to the direction of the displacement. So notice here again on the figure na our force exerted is going to the opposite direction with the displacement. So work is negative here because F cosine of phi is negative for, we have again here, our angle is greater, if our angle is greater than 90 degrees, but less than 180 degrees. So again, dapat greater than 90 degrees. It's because if we put greater than or equal, so if your angle will be equal to 90 degrees, so the cosine of 90 is 0. And also, our F cosine phi will be 0 if our angle will be equal to 90 degrees. So our angle must be greater than 90 degrees and also less than 180 degrees, so that our work will be, or F cosine phi will be negative, and also our work will be negative. So we have here our force diagram as well as our situation indicating na the force or the direction of the force is opposite to the direction of our displacement. So that's why our work will be negative. And then for letter C, we have here our force F is perpendicular to the direction of the displacement. So it means na the force does no work on the object. So again, since our angle phi is equal to 90 degrees, so if we will cosine of 90 degrees is equal to 0. So even if we have like a displacement S, so no matter how big your displacement is, if our force is exerted is perpendicular to the direction of displacement, so we have no work done on the object. So that is how we will know if when our work will be positive, when our work will be negative, and also when will our work be 0. Okay, so we have here and also an illustration. So in illustration, or in figure 6.5, we have here a weightlifter does no work on the barbell as long as he holds it stationary. So the weightlifter exerts an upward force, but because the barbell is stationary, so stationary means na it is not moving, so the displacement is 0. So even if you have, let's say for example, you're exerting 1,000 newtons na force, but since you are holding the barbell, you are just holding the barbell, so there is no displacement. So 0 ang imong displacement. So even if you have like a force, so still our work will be 0. So if our displacement is 0, and if you have you are exerting an upward force, so still our work will be 0. But if here we have in letter A, if a weightlifter lowers a barbell to the floor at a specific displacement S, so that is the time na we will be having, or there is a work done by the weightlifter on the barbell. So as long as there is a displacement, and also you're exerting a force on the object while the object is having a displacement or a change in position, so there will be work done on the object. Okay, so another example number 2 is still all about work. So we have here a farmer hitches her tractor to a sled loaded with firewood and pulls it a distance of 20 meters along the level ground. So the total weight of the sled and the load is 14,700 newtons. So also the tractor exerts a constant 5,000 newtons force at an angle of 36.9 degrees above the horizontal. And then we have a 3,500 newtons friction force opposes the sled's motion. So we need to find the work done by each force acting on the sled, and also the total work done by all of the forces. Okay, so before we will solve for the work done by each force acting on the sled, we will first determine what are the forces acting on the sled. So here, on the free body diagram in letter B, notice now we have the normal force. So normal force again is perpendicular. So it is located right here. And also, we have obviously the weight of the sled and the load, which is straight downwards. And then we have the tension force, since the tractor is using a chain, we have right here, to pull the sled that is loaded with firewood. So the tension force is located right here. And then we have the last one is the friction force, which is parallel to the surface or parallel to the sled and opposite to opposite in direction sa kung asa mo slide or asa padulong ang imo ang sled. So in this case, it is going to the left. Okay. So again, we have the normal force, we have tension force, we have the friction force, and we have the weight. So these are the forces acting on the sled. So now, we need to find the work done by the normal force. We need to find also for the work done by the tension force, work done by the friction force, and the work done by the weight. So because we are asked to solve for the work done by each of the forces acting on the sled. And after we get the work done by each of the forces, is we need to solve for the total work done by all of the forces. Okay. So for the given values we have right here, the first one is the distance, which is 20 meters. And then we have the weight, which is the total weight of the sled and the load. So it is 14,700 newtons. And then we have the tension force, which is 5,000 newtons at an angle phi, which is 36.9 degrees. And the last one is the friction force, which is 3,500 newtons. Okay, so we will start with the work done by the normal force. Okay, so to solve for the work done by the normal force, so work done is equal to force times the distance or the displacement. So in this case, our force is our normal force. So we have normal force times the displacement. So notice here na si normal force is perpendicular or 90 degrees with regards to our surface of contact. So we have the normal force times the distance times the cosine of 90 degrees, which is equal to 0. So again, since cosine of 90 is equal to 0, so the work done by the normal force is 0. So we proceed with the work done by the tension force. So we have again tension force times the distance times the cosine of the angle phi or phi. So we have tension force here is 5,000 newtons times the distance, which is 20 meters, times the cosine of, we have here angle 36.9 degrees. Okay, so if we will calculate that one, we have 5,000 times 20 times the cosine of 36.9. It is equal to 79,968.47. So again, the unit is in terms of joules. So the total the work done by the tension force is equal to 79,968.47 joules. So we are now done with the work done by the normal force as well as the tension force. So we will proceed with the work done by the friction force. So we have the friction force times the distance times the cosine of the angle phi. So we have our friction force is 3,500 newtons times 20 meters. Now times cosine of, okay, so let's go back to the previous slide. Notice na si friction force is moving along the negative x-axis. So the angle of the friction force is, we have right here, equal to 180 degrees. So it is equal to cosine of 180. So the work done is 3,500 times 20 times the cosine of 180, which is equal to negative 70,000 joules. So that is the work done by the friction force. And then the last one, we have the work done by the weight. So we have weight times the distance times cosine of the angle phi. Okay, so weight is 14,700 newtons times 20 meters times the cosine of, okay, so again, let's go back to the previous slide. Weight here is along the negative y-axis. So from here up to here, the angle is equal to 270 degrees. See, friction force is 180. So see, weight is, the angle of weight is 270 degrees. So now we have, again, the work done by the weight is 14,700 times 20 times the cosine of 270, which is equal to 0. Since again, cosine of 270 is equal to 0. So if you multiply that with 14,700 times 20, so it's still 0. So again, we are now done in solving for the total work done by each of the forces acting along the sled. So we have again the work done by the normal force, the work done by the tension force, work done by the friction force, and then the work done by the weight. So since we are done solving for the work done by each of the forces, so the next one is to solve for the total work done. So for the total work done, it is the sum of the work done by the normal force plus the work done by the tension force plus the work done by the friction force, and then plus the work done by the weight. So substituting their values, we have work done by the normal force is 0, plus on the tension force we have 79,968.47 joules, plus the work done by the friction force is negative 70,000 joules, and then plus the work done on the weight is 0. So calculating this one, our total work is equal to 9,968.47 joules. So this is our total work done by all of the forces that is acting along the sled. Okay. So we are done with the second example. Okay, so now we proceed with the kinetic energy and the work energy theorem. So the total work done on a body by the external forces is related to the body's displacement. That is, to the changes in its position. So also the total work can also be related to the changes in the speed of the body. So not only the displacement, but also we can relate work in terms of the changes in the speed. So we have here the following scenarios. We have 3 different scenarios. For letter A, we have here a block that slides to the right on a frictionless surface. So if you push the block to the right, so the net force on the block is also to the right. So which means that the total work done on the block during a displacement is positive. So if our total work done on the block is positive, what will happen to the block is the block will speed up. Okay, but for letter B, if we will push the block to the left while it is moving or while it is sliding to the right, so what will happen is the total work done on the block during a displacement is negative. So what will happen to the block is the block will slow down. And then for letter C, we have here, if you push straight down on the moving block, so the net force on the block is 0, or the total work done on the block during a displacement is 0. So what will happen on the block is the block speed will stay the same because there is no work done on the block, or since the net force or the force on the block is 0. So that is how we would relate the work done with the changes in the speed of the body or on the object. Okay, so if we will consider a particle with mass m moving along the x-axis under the action of a constant net force with magnitude f directed along the positive x-axis. So the particle's acceleration is constant and given by Newton's second law, which is F is equal to the mass times the acceleration along the x-axis. So suppose the speed changes from v sub 1 to v sub 2. So v sub 1 is the initial speed and v sub 2 is the final speed, while the particle undergoes a displacement s, or we have d, which is equal to the final displacement minus the initial displacement from point x sub 1 to x sub 2. So if we will be using a constant acceleration equation, so the equation that we will be using is, we have v sub x squared minus vox squared is equal to 2 times a sub x times x minus x sub o. So this is the fourth equation on the kinematic equations along the x-axis. So this is, or we will be using this one as our constant acceleration equation. So now if we will replace vox by v sub 1 and v sub x by v sub 2, as well as x sub o by s or d, so if you will replace those by v1, v2, and s or d, we have now, so v sub x will become v2, so this is v2 squared minus v1 squared is equal to, we have again 2a sub x times d. Okay, so if we want to solve for the acceleration on the x, we need to divide both sides with 2d. So that it will be cancelled out. And then we are left with a sub x. So a sub x is equal to, we have v2 squared minus v sub 1 squared divided by 2d. Okay, so now, if we will multiply both sides, so we will multiply both sides with m. So multiplying both sides with m, multiply here m, and also here by m. So we have m times a sub x is equal to, we have m times, we have v2 squared minus v1 squared divided by 2d. Now take note na m times a sub x is equal to, we have here force of the Newton's second law. Okay. So now, the last step is to multiply both sides with d. So d will be cancelled out right here. So we have f times d is equal to we have 1 half m times v2 squared minus 1 half m times v1 squared. Now, notice na, di ba, we have force times distance is just the work done. So, the work done is equal to, we have 1 half mv2 squared, or 1 half times the mass times the final speed quantity squared, minus 1 half times the mass times the initial speed quantity squared. Okay, so this is our equation right here. But take note na kinetic energy, or the definition of kinetic energy, we have K is equal to 1 half times m times v squared. So, from the previous slide, di ba previous slide we have the work done is equal to 1 half m times v2 squared minus 1 half m times v1 squared. So, since kinetic energy is equal to 1 half times m times v squared, so we have here our work energy theorem. So the total work done is equal to, we have the final kinetic energy, which is this one, minus the initial kinetic energy, which is this one. Or it is the change in kinetic energy. Okay, again, when we say change, it is final value minus initial value. So in this case, if it is change in kinetic energy, so it must be final kinetic energy minus initial kinetic energy. So that's why we can relate kinetic energy to the work done by the net force. So the work done by the net force on a particle is equal to the change in the particle's kinetic energy. So by the way, kinetic energy is a scalar quantity. So again, scalar quantity means that it has magnitude only. So it does not depend on the direction of your object, because again, kinetic energy is a scalar quantity. So it only depends on the value or the magnitude of the mass and the speed of the object. Okay, so now we have three equations for work na. So the first one is the straight line displacement, work done along the straight line displacement, which is equal to force times distance or displacement. And the second one is we have is equal to force times the displacement times the cosine of the angle phi or phi. So we have now three equations that we can use to solve for the total work done. So again, depending on what are the given values provided by the problem. So we cannot use the work energy theorem if our given are just in terms of force and displacement. So we can use the work energy theorem if our given are in terms of mass and also the speed, the initial and final speed of the object. Okay, so we have here an example. So let's look again at the sled and our results in example 2. So in example 2, we have, this is our example 2. Okay, so this is our example 2. Okay, so let's go back here. So suppose the sled's initial speed, V1, is 2 meters per second. So we have right here, this is our initial speed. So what is the speed of the sled after it moves 20 meters? Which means na we are asked to solve for the final speed of the sled after it moves 20 meters. Okay, so how can we solve for the speed or the final speed of the sled after it moves 20 meters? Okay, so diba, our given, the given that is provided right here are, we have the initial speed, which is 2 meters per second, and also the distance, which is 20 meters. Okay. So we are asked to solve for or find the final speed v sub 2. So again, recap, the work energy theorem states that the total work done is equal to the change in kinetic energy, which is equal to the final kinetic energy K sub 2 minus the initial kinetic energy K sub 1. Okay. So, since V sub 2 is on K sub 2, which is, diba, K sub 2 is equal to 1/2 times the mass times V2 squared. So we need to solve first for K sub 1, and then we have now the value of our total work done. Katni si total work done. Total work done is this one right here. So let's look at the previous slide. So this is our total work done for example number 2. So total work done is 9,968.47 joules. Okay, so we have the total work done. So we need to solve for K sub 1 first, or initial kinetic energy, before we can solve for the final kinetic energy. But here, to solve for kinetic energy, initial kinetic energy, I mean, so diba, K sub 1 is equal to 1/2 times mass times V1 squared. But we don't have any value for the mass. Now, take note na in the previous, in example number 2, we are given the weight of the object, or the weight of the sled and the load, which is 14,700 Newton. So we have the weight, which is 14,700 newtons. So, to solve for the mass of the sled, take note na weight is equal to mass times gravity, or the acceleration due to gravity. So, to solve for the mass, we divide both sides with g so that it will be cancelled out. So, we have the mass is equal to the weight of the sled divided by the acceleration due to gravity. So we have weight is 14,700 newtons divided by g is 9.8 meters per second squared. So 14,700 divided by 9.8 is equal to 1,500, and then the unit is in terms of kilograms. So this is now our mass. This is the mass of the sled. Okay, so again, take note na Newton comprises of kilogram times meter per second squared. So since we have meter per second squared on the denominator, so it will be cancelled out, and then we are left with kilogram or kilogram. So again, we have now our mass, which is equal to 1,500 kilograms. So we can now solve for the initial kinetic energy. So we have 1/2 times 1,500 kilograms times V sub 1 quantity squared, or we have 2 meters per second quantity squared. Okay. So we have again 1/2 times 1,500 kilograms times 4, and then the unit becomes meter squared per second squared. Okay. So now the initial kinetic energy is, we have 1/2 times 1,500 times 4 is equal to 3,000. Now, what is the unit for energy? So the unit for energy is the same as the unit for work, which is still joule or joules. So the unit for kinetic energy is in terms of joules. Okay. So initial kinetic energy is 3,000 joule. So we have now the total work done. So we are basing here sa atong work energy theorem na equation. So we have the total work done. We have now our initial kinetic energy. So now we can solve for the final kinetic energy. So again, we have here total work done is equal to K sub 2 minus K sub 1. So to solve for K sub 2, we need to transpose negative K sub 1 to the left side of the equation. So K sub 2 is equal to the total work done plus K sub 1. So we have our total work done, which is 9,968.47 joules, plus our K sub 1 is 3,000 joules. So K sub 2 is, we have 9,968.47 plus 3,000. So K sub 2, or our final kinetic energy, is 12,968.47 joules. Okay, so we have now our final kinetic energy. But again, we are asked to solve for V2, or our final speed. So to solve for the final speed, the last step, we have K sub 2 is equal to 1/2 times m times V2 squared. Okay, so we need to divide both sides with m and multiply both sides by 2. So that we have here, this will be cancelled out. And also we have 2 times 1/2 is just equal to 1. So we have V2 squared is equal to 2 times the final kinetic energy divided by the mass. Okay, so we have here still squared left in our V sub 2. So we need to get the square root on both sides para ma-cancel out si squared and the square root. Okay, again, square root is equivalent to the power of 1/2. So, to solve for V sub 2, okay, here, to solve for V sub 2, it is now equal to the square root of 2 times K sub 2 divided by the mass. Okay, so substituting their corresponding values, we have 2 times K sub 2 is 12,968.47 joules divided by the mass, which is 1,500 kilograms. Okay, so if we will calculate this one, we have the square root of 2 times 12,968.47 divided by 1,500. So it is equal to 4.16. And then the unit will be in terms of meters per second. So the final speed of the sled after it moves 20 meters, so this one right here, V sub 2 is equal to 4.16 meters per second. So that is our final speed of the sled after it moves 20 meters by using the formula for the work energy theorem. So that is our example in continuation with example number 2, in which we relate the equation for the work energy theorem. So that's it for our discussion for today.